Thank you, Chandrakant. And thank you for hanging out here till the evening. I just went to take a nap. I'm almost falling down. I don't know how you guys are surviving. So thank you for being here in this last afternoon. So what I'm about to lecture on is maybe Gate's Mazer or Lean-Rappaport, two big mountains. And I think Diamond M take a photo of this. Okay. And I'm taking a photo of that. Okay, so it's really a very, very fast overview of Diamond M, which has several sections, 8, 9, 10, 11, 12, where it does canonical models, etc. I'm just trying to do enough to provide some service to some of the other lecturers. One of them requested, Samuel, the Q expansion principle. So my goal is to get to that. So, okay, let's see how we do. And I know that this talk has one extra page, so it's not going to finish in an hour and a half. But let's see, I put the notes up on the web page. So fortunately, the Q expansion principle is in the last 5 minutes. So I might take 5 minutes extra, warning you. Okay, so lecture 4. Integral models or canonical models and the Q expansion principle. Models of modular curves, of course. Right, so let's get straight into it. So define following functor F1n. I'll also raise the level of language a little bit, and there may be some imprecise statements. For example, I've noticed some lectures started using the word nice for various varieties with 12 adjectives in them. And so maybe I'll also start doing that. In the notes, I've tried to fill in some of the things. Notes means my handwritten notes. I hope you can read my handwriting. Okay, or maybe I'll read out some things rather than saying the word nice. All right, so Z1 over n schemes. Functor from this category, 2, so n is greater than or equal to 1. Usual level. Sets where we're taking a Z1 over n scheme to the isomorphism classes of pairs E, supposed to be a script P, but I don't know how to write it without it looking like a Weierstrass P function. Maybe just a normal P. So this is an elliptic curve over S, or a family of elliptic curves. Okay, so this has some formal definition, which maybe I'll read out. So a smooth, proper group scheme whose geometric fibers are all elliptic curves. Okay, so such things maybe I will not say too often. And this is a point of exact order n. So that means that if you pre-compose this with the map spec K to S, in other words, you take a geometric point, then the composition all the way into EK, that element in EK has exact order n. Okay. So this is supposed to mimic what we had already done in the first lecture. We had taken an elliptic curve and a point of order n. Now we're working over any base. Okay, so these are the objects, f of s, f1n of s, and morphisms. So if f is a map of schemes as to t, fiber product, you get this move isomorphism classes. So write something here. F is a map from S to T, morphism of schemes. You define F1 of n, that's supposed to be a script F every time, of F of be a map from F1 n of t to F1 n of s, so contravariant functor. It's flipping arrows, taking EP to this particular elliptic curve, this point of order n. What is E? S, just the base change. E was an elliptic curve over T. You have a morphism from S to T, so you just take the fiber product, base change. Similarly, some diagram for the point of order N. ES. Okay, so just base change. So this defines a functor. Contravariant functor. And the main theorem, due to Agusa, and written up in Jean Rappaport, Katzmazer, etc. Let me put some numbers here so that you can really stare at these statements, corresponding statements, at least in Diamond Im. The numbering is from Diamond Im. Should say this is chapters 8, 9, and 12, basically, or sections 8, 9, and 12 of Diamond Im. I move from Diamond Sherman to Diamond Im. And the first 7 sort of sections, I sort of gave an overview, a slower overview, using Diamond Sherman. Okay, so this is theorem 8.21 in Diamond In. Suppose n is not 1, 2, or 3, then there exists a smooth Z1 over n scheme. This functor is representable, Y1n, representing F1n, i.e., functor is just given by the S-valued points of this scheme. Should say that, yes, I said it's Z1 over n scheme. So some people shorten this and write this as Y1 n of S, S-valued points of the scheme S, shorthand for writing these morphisms. I think so. I don't think so. Okay. All right, so now there's some properties of this scheme which I will read out to save some time. So Y1 of n is smooth, so relative dimension 1, and it has irreducible geometric fibers. Okay, but for now, let us not. I'm trying to get to the Q expansion principle, so just using some sort of facts along the way as black boxes. So proof. I was a bit surprised to learn this is due to Agusa. Everybody seems to acknowledge him. I didn't know this, but it was always Jean Rappaport or Katzmazer. So Agusa, but Diamond Im refer to these people. Okay, so now let's take S to be C. Complex numbers, compare with what we had before. So this says that you get a bijection between the C-valued points, be a script Y, and our old modular curve Y1n. Right? plugging in S equals C, get this. It's just the elliptic curves and points of order n over the complex numbers, which we just done. Up to isomorphism, I should have written, but I forgot to say that. Okay, so good. Because of this fact that the C-valued points are exactly these complex points of this modular curve, I mean, this modular, this Riemann surface, we say that y1 of n is a model. It's almost over Z even, it's an integral model, but Z1 over n is still considered integral. So it's a sort of an integral model of our old modular curve y1n, which appeared in the first lecture and in many, many talks. Okay, and one more remark. Taking S to be the other extreme case, maybe, or one extreme case. Well, what if you just take S to be y1n itself, and you take the identity morphism in the Helm space, corresponds to a particular elliptic curve. And that's the so-called universal elliptic curve. This is a point of order n. And by some general nonsense, this has the property that every elliptic curve over any base t can be recovered by pullback from a morphism, by a morphism from t to y1n. Every EP over T, some scheme T, is obtained by pullback following picture. There exists a morphism from T to y1n, T-valued point. So this corresponds to this pair. And we have this. The universal was the base here was y1n. And E is obtained as this fiber product. Okay, so we also have this family of elliptic curves living over the modular curve. All right, so for the Q expansion principle, turns out to be more convenient to work with a slightly different moduli problem. So maybe I should say that, okay, I'll say that maybe later. What happens when n equals 1 and 2 and things like that, and what about gamma naught n? Make some comments about that later. Okay, so variant. Again, I'll follow the numbering in diamond M. Giving a point of order, exact order n, is giving a closed immersion of the group scheme Z mod n to script E. So that is, and we could take some sort of other embedding from some other group scheme. And if you do that, you get another moduli problem. And this is the one that's used by other authors. Sometimes I think Gross has mentioned a few times here. So the slight advantage of that is that apparently the model is defined over Z. And I should say that here we're really trying to do integral models, whereas I think Jan mentioned some canonical models from Shimura, which are defined over Q. So this is, I guess, one step further than that. Right, so giving a point of order n is equivalent exact order n is equivalent to giving closed immersion inside E group schemes defined over S. So the variant is that instead of looking at this embedding, why not look at the embedding of mu n inside E? Consider instead embeddings from this group scheme to ES. So this also turns out to be representable, but it has the apparent, well, for us, not just apparent, we'll see how it's used. It has the advantage that this group scheme is defined over Z. A group scheme, the model is defined over Z. Then the resulting functor is representable again. And even defined over Z. This is representable by the following scheme. Let's give it a name. It calls it Y mu n. So the mu is different from my mu. The blackboard bold mu, whereas they just write a single mu for some reason. But anyway, let me just use their notation maybe. So Y mu n over Z. This is a Z scheme. Okay, so again, we have, if you look at the C points, turns out to be in bijection with Y not n, Y1n, sorry. This time, we should say a little bit about what this bijection does. So remember, we had these isomorphism classes of E tau, C modulo the lattice spanned by 1 n tau. And we had this point of order n. This time, this corresponds to here. Again, E tau. The first coordinate is just an elliptic curve, but the second coordinate is an embedding of mu n into E. So the second coordinate is given by taking this primitive root of unity, e to the 2 pi I over n, to 1 over n plus lambda tau. Slight change of perspective. Tau belonging to the upper half plane. Okay, so we'll ignore that for now, but we'll need it right at the end. So I'll carry this variant along in the discussion, because ultimately we want to look at a Z-valued point of some scheme. And the scheme is defined over Z1 over N, you can't do that. Okay. Oh, so one more remark here is that apparently this scheme is not, when you base change to Z1 over N, you don't actually get the same scheme as the old script Y1 over N. You have to do further base change to zeta N, I mean, join nth root of unity, this one, and then these two schemes become the same. So I won't write that maybe. Okay, remark. What about for N equals 1 and 2 and 3? Well, things are not as good. There's some torsion here, and you only get force moduli schemes. This functor is not representable anymore. But on algebraically closed fields, you do get bijections. So you can think of that as the definition, more or less, of a coarse moduli scheme. For example, you still have that Y1 n of C is in bijection with Y1 n. C, but this bijection may not hold over other rings, over other schemes. And similarly, you could, okay, so all of this generalizes. Well, okay, not quite. So for y naught n, it's a bit trickier. Y naught n has a bit more torsion. For example, the negative identity element is always in y naught n, right? This causes some problems. So y naught n, the functor is not representable again. Similarly, get force moduli scheme. Y naught of n. This is for all n. Okay, but we don't need that much in the Q expansion principle, just a remark for us for now. It's also defined over Z1 over n. And n is greater than 3. And again, for n less than or equal to 3, you can do some tricks and get a coarse moduli scheme. So one of the tricks actually is, and I hate to admit this, is it uses diamond operators. So to get from y1 of n to y naught of n, you have to do some quotients, right? So, okay, which is why I'm not writing anything more there. All right, so here. So now the question is, what about the Heck operator TP? So remember, we defined TP just as an abstract double coset first, then we decomposed it as a disjoint union of single cosets, finite union, and some time showing the finiteness. Then we made that operator act on various things. It acted on modular forms and cusp forms. It acted on modular curves. It acted on Jacobians, right? It acted on various things. It can make it act on even more things. One can ask that in this setting, can you define TP? Slightly more abstract setting, and you can. This is done in section 8.3 of Diamond and Nim, and I'm not going to do it. So, but I mean, we had some sort of formula for TP finally, which was very nice, if you remember. Take an elliptic curve and a cyclic subgroup of order n to E mod C and things like that, right? We had some moduli interpretation of it that generalizes. Okay, so unfortunately, I'm not going to be able to do many things about models of everything in sight. So for example, I'm completely going to skip models of Jacobians, so that's a very interesting topic, especially for the bad reduction. I mean, for the reduction of the Jacobians, when it has good reduction, bad reduction. What do the fibers look like, etc. Get some semi-abelian varieties. Okay, so let's move on to chapter 9. That's all I wanted to say from chapter 8. Generalized elliptic curves. So we want to compactify, and for this, we need something a little bit more general than an elliptic curve. And this is what it's, this generalized elliptic curve. And I think the motivation in Diamond Nim is very nice. Not really a theorem or anything. So let's do this motivation. It's maybe more useful than the actual theorems. Okay, so I'll try and do that. So the first remark is that even though many of you have learned elliptic curves for a few years, you probably haven't yet realized that C mod lambda tau can also be written in multiplicative notation. In other words, it can be written as C star modulo Q to the Z. Q is e to the 2 pi I tau. On the upper half plane. Right, you can see that one goes to e to the 2 pi I. This is just the map Z goes to e to the 2 pi I Z. Induced by that. One just goes to 1. Sorry, Yes, 1 goes to 1. And tau goes to e to the 2 pi I tau. So the generator here you get is q. So there's actually an equation of the elliptic curve. I think several times now in this workshop, equations have been written down for on this side, but you can also write down an equation using the parameter q. It's called the Tate curve. So let's do that. So I don't know how people remember these things. I certainly don't. I don't work in this on a daily basis either. Write these formulas down. This is a curve over spec Z Laurent series Q. Nice to see that sometimes Tate descends to the level of Ramanujan. These formulas look like something that he might have done in 1920s. I think I missed a 1 in the notes. Please add that. This typo here. 5n cubed. 1 minus q to the n. Q to the n. So there's an equation for this elliptic curve in terms of the parameter q, and that is those are the formulas. Called the Tate curve, the Tate curve model of this elliptic curve. And it'll come up a lot, EQ. Okay, so what is this motivation in diamond im? So what they do is, they look at what happens as tau tends to infinity. As tau tends to infinity, we know this very well when you map complex plane, upper half plane to the disk, for instance, then as tau gets larger and larger, q tends to 0, right? And what happens to EQ? Degenerates to the following, just see what happens. Notice this is starting from 1, not 0, though I missed it in one of my formulas notes. These are all becoming 0. A4 and A6 become 0, and you get the following equation. Equals x cubed. If you try and graph this, and I actually physically did this on Google. If you have a laptop now, you can try it yourself. For some reason, I had to do it in 2 parts, x greater than 0 and x less than 0. If you have a laptop open, you can just press graph this. The graph, if you try to graph y squared equals, sorry, y squared plus xy equals x cubed. The affine curve. So Google complains a bit, but then maybe some software is needed. I don't know. Did this a week ago. So you get the following picture. It's roughly like this. So even though the curve was smooth, for q not equal to 0, as q is tending to 0, you wind up getting a singularity. And you wind up getting a double point. And so what you should think of this as roughly is as a P1, where you go, when you go one way on it, you're at 0, and then when you go another way at, you're at another point, let's call it infinity. Okay, so you're gluing together 0 and infinity, so a double point. There's a singularity at x equals y equals 0, it's a double point. So let's write, did I call the curve C? No, I didn't. It degenerates to this. Let's give it a name, C. So let C reg be the smooth part. So now you have P1 and you've taken away a 0 and infinity, so you're left with a GM basically. And you get an addition operation, you get an action of C reg cross C. You can multiply a root of unity on any of one of these P1 points, wind up with something in P1. Okay, maybe I should not say that. This actually comes from the group law on the Tate curve by taking Q equals 0. So this equation here has some group law formulas. And if you just take those formulas with Q equals 0, you get an action of C reg on C. Okay, so now group law. Q equals 0 in the group law on EQ. Moreover, you can extend this to the normalization, this group law, in the following way. You have this action of C reg on C. C reg was just GM, we just said that. Normalization of C is P1. Right, another arrow here, though I shouldn't. One arrow for the product going down to the product, but okay. The normalization. And similarly, here we have the normalization. So this action at the bottom extends to an action up here, and this is just the silly action, the one I was referring to incorrectly for this. I need it up here now. The GM acts on P1 just by multiplying by a non-zero number. In other words, this action extends. Okay, so this picture here is called what's called a Néron one-gon. This C plus, which has an extension like this, the action to the normalization. So it's a polygon with one side. You'll see why in a second. Pictures, this word has certainly been used before by Jan, and there have been pictures about it, more general context. So let's try to get to the more general thing. The definition. The pair C, find the one gone more generally. We find Néron n gone. And greater than or equal to 1. But only over an algebraic closed field. By the way, everything here was happening over the complex numbers. There were taus and things, yeah, complex numbers. Okay. Should have said that maybe. All this theory was over the complex numbers. So there's a Néron one gone over the complex numbers. But you could now define a Néron n gone over any algebraic closed field. I'll give it a name. As the space, so I have to go over there. It's sort of just nice to look at the picture, and the picture has already been put up. Other talks. Forget the last word, but hopefully my grammar is okay here. As Cn equals, so yeah, it seems to drop curves and drawing straight lines here to make it more look like a polygon. Here you have some singularities. So it's basically a disjoint, I mean, it's a not a disjoint union, it's a union of P1s. So n irreducible components, each isomorphic to P1. And they're glued together, so they're indexed by Z mod n. plus n ordinary double points. Actually don't know what the word ordinary means. Think about that, but just write it. Okay, n ordinary double points, and we require that under the normalization, just a disjoint union of these P1s. The points infinity on the ith component and infinity I plus 1, and 0 on the, infinity on the ith component and 0 on the I plus 1th component, they map to the same point. So this is 0, 1, and infinity of the other. Maybe infinity of the ith component and 0 of the I plus 1th component, they map to the same point. As you can see why that's a neuron 1 gone now. There's only one side there, and 0 infinity were glued together. So just as in the case of this motivation here, the one gone is a similar picture. So this is not a plus, but an and. So we want to define a plus now. Action of the regular points on Cn. So this is what they say. I'm just going to say it. You just define it so that it makes some diagram commute. Commutity of the following diagram. So C reg, if you just drop these points, drop these singularities, then you just get a disjoint unions of GMs. And that is isomorphic to the n reg. And up here, well, okay, you have C. So we want to define this plus action. Up here you have the normalization. And here you have the, it's not completely obvious, this action. You might think it's just component wise, but it's not. There's some subtlety here. Subtlety is that not just GM acting on P1 component wise, something like Xi, Yj goes to Xy, you multiply the two numbers, but you move the component to I plus j. That's a little strange, but that's what it is. Basically, I think want your points of order to n to meet every component. So you need to sort of do some cyclic thing. Okay, so apparently there's a plus which exists, which makes this diagram commute. And I haven't thought about it much, but just assume that. Anybody has remarks or comments, wants to fill in anything intelligent, please go ahead. Happy to learn. The same paper I mentioned, BG, in my last lecture. We actually wrote down the structure of the endomorphism algebra of not just the abelian variety attached to a form, but Scholl's motive attached to a form of a higher weight. The weight is higher, you don't have an abelian variety, you have a higher weight. And they're sort of forced to study Néron n-gons a lot, maybe 15 years ago. I haven't thought about them since then. Because you had to sort of define the endomorphisms also at the cusps, some modular interpretation. Okay, so definition, we finally define a generalized elliptic curve. Yes, sorry. Yeah. Is there a problem? What's the problem? Yeah. You mean how is plus defined? There are too many options that make this diagram commute? Is that what you're saying? Yes, okay. That's okay. Yes. In fact, even in the case of one gone, I swept that under the carpet. There is a specific isomorphism there that is in diamond-dim and that is chosen. And perhaps they're doing the same thing here. Will that make you happier? Okay, thank you. Yeah, I didn't realize that was so important because there's a whole bunch of formulas and I wanted to skip them. So yes, you're right. In diamond-dim, when he defines the Néron n1 gone, he picks a specific morphism. Okay, so maybe this choice of R, I'm dropping a lot of notation. So actually, they do say it's a choice of an R and a lift of R to the normalization. I'm dropping those words. Maybe they're important. Okay, thank you. All right, so let's come to the definition of a generalized elliptic curve. Over S is a pair E plus, where E is a group scheme over S, not necessarily smooth. And plus is an action of E reg on E. Such that plus makes E reg a group scheme, a smooth group scheme, commutative group scheme over S. On E, I already said it acts on E. And some other technical conditions, I don't know. Okay, so this one's important. The geometric fibers of E plus are either elliptic curves, smooth, or Néron n-gons. Okay, so a generalized elliptic curve is almost an elliptic curve, but not quite. The action is of the smooth part that makes E reg into a commutative group scheme. And you require that the fibers here are geometric fibers or work over an algebraically closed field. You either get elliptic curves or Néron n-gons. This is the definition of a generalized elliptic curve. Okay. So some remarks which I won't write down is that if you have a generalized elliptic curve which is smooth, then you just get an elliptic curve in the old sense. That's one remark. And the second remark is that, okay, maybe I'll skip that one. All right, so back to our example, or so with the Tate curve. This is example 9.2.1 in Diamond IM. So consider the Tate curve again. And this time, let's consider it over spec Z power series Q, Taylor series Q rather than Laurent series Q. Completely clear to me why. I think I know why they do this. It'll appear right at the end. So look at those formulas. You notice there was a 1 minus Q to the end in the denominator, but you expand that with the geometric series expansion, you don't really get any negative powers of Q, right? So you can also think of it as a scheme over spec Z power series Q. We'll need that because, okay, I'll show you where we'll need that. So let's look at it as a scheme over that and consider, let's define EQ reg to be the complement of X equals Y equals Q equals 0 in EQ. That is spell complement with an E and an I. Always make this mistake. E? Thanks. Yeah, compliment you for knowing that. All right, so what's the group law? So the group law on EQ over spec, this is just a technical point, but the group law over Z Laurent series Q extends to one over Z Taylor series Q. This is this fixed scheme now. And moreover, if S, little s now, is a geometric point, okay, that'll be closed field, geometric point, then it's a little less. It's then what do you get? You get, you in fact do get either an Heron n-gon, or we just saw that, or a elliptic curve. So in the case where S of Q is 0, Q is equal to 0, you get E Q over K plus K plus S. And Heron 1-gon. And when S of Q is not 0, you wind up getting a normal elliptic curve, just a usual elliptic curve. Usual plus. So in case the complex numbers, you just wind up getting C star modulo Q, where Q is e to the 2 pi I tau. And that's just C modulo lambda tau, the usual elliptic curve. K is equal to e tau. Okay, so here's the basic example of a generalized elliptic curve. It's the state curve. When Q is not 0, you get a usual elliptic curve, and when Q is 0, you get a Néron n-gon. Okay, so good. So now that we have this notion of Néron n-gon defined somewhat formally, we can go back to canonical models or integral models, but for the compact curves. What about those? Do they have models? So we need to generalize these functors a little bit. Instead of taking our S-valued points of this functor to be just usual elliptic curves, we're going to take the valued points to be generalized elliptic curves and hope that's representable. So can regard. Okay, so new section here. In chapter 9, this is section 9.3 of Diamond. Okay, so over the complex numbers, the motivation for this is that that curve x1n that we had before, h mod gamma 1n, and compactified with the cusps, and I even wrote an explicit set of sort of representatives for the cusps. We can actually associate to each one of these cusps Néron, I shouldn't say n-gon because it's not always an n-gon, but a Néron m-gon. M might depend on the cusp. So let's write that down. Can regard x1n as a moduli space. Okay, so this time the points are going to be in bijection. Bijection with Néron n-gons, or generalized elliptic curves. We had this notation of square bracket EP, but E is no longer E is no longer an elliptic curve, it's just a generalized elliptic curve. E is a point of order n. So we've already done this, just over the complex numbers again, we've already done this for the open modular curve, right? We've said that this is basically E tau, and this is 1 over n plus lambda tau. But what do you do at the cusps? So at the cusps, I'm just blatantly copying the formula from Diamond Im. So remember, in my third lecture, I said that the cusps were parameterized by classes, where the first classes of ordered pairs, where the first coordinate was in Z mod n, and the second coordinate was in Z mod the GCD of C mod D, C comma D, GCD of C and D. Sorry, C and N, there's no D. Sorry, C and N. Star. So if you remember, this was this modulo plus minus 1. That's why the square bracket. So this corresponds to not an elliptic curve now. This is a cuspidal point. It corresponds to the following n-gon, and I was a little confused about what they wrote here. So n C over n-gon. UCD. So it's not always an n-gon. EP. What was a bit confusing is this point of order n. So E is just a Néron n-gon, so it's Cm, where m is this number. But P was the following, they have the following formula for P in terms of C and D, and that is, they just write this, e to the 2 pi id over n, and then they write C over Cn. So that formula, maybe people can comment on it. It looks like they're specifying the value of the n torsion point at the C by GCD coordinate. But it's not so clear how they're extending it to the other coordinates. Is it 1 everywhere else, or is it notation. I really thought about it. Anyway, there's some explicit bijections. Explicit formula for the point of order n. Anyone have any comments on this? Okay. Yeah. Yes. Yes, yes, yes. That point, everywhere else you put one. You put one on the other. What you have to have other coordinates, right? Oh, you don't need it. I see. It's just join union. Okay, thank you, thank you. That was confusing me. Great, thank you very much for that comment. Okay, so let us come to the definition of its more generalized functor. So G1n to define the following functor from Z1 over scheme, Z1 over n schemes. Sets. Where S goes to isomorphism classes of, again, script E and script P, but I'll not write that, so Roman P. This time E is a generalized elliptic curve. And P is an exact point of exact order n, going into E reg. There's another condition here, and I won't write it, maybe, slightly technical. It says that for all geometric points K, so for all geometric points from spec K to S, if you further compose, the image of the resulting immersion from Z mod n over K to EK reg meets every component. Oh, I think I did write isomorphism classes, so I didn't have to go modular isomorphism last time. Okay, so it's roughly this. But the point is that one is taking generalized elliptic curves and generalized points of order n. Okay, so here is the theorem. This is all like really magical stuff for me. I hope people even dream of such things. It's really remarkable. So for n greater than 4, turns out that this functor is again representable. By supposed to be a script X. People have various notations in this conference. I don't know. It looks more like a chi, but okay, X1 n over Z1 over n. It's smooth, etc. A bunch of properties here, which I won't get into. So again, this moduli problem now is representable. And this time, again, the scheme is defined over Z1 over n and not Z, and there'll be a variant which will be defined over Z. Similarly, can define force moduli scheme X naught n for n greater than or equal to 4, and also X naught n and X1 n. And using some diamond operators to get down to X naught n, but some special tricks for X1 n and X naught of n for n less than or equal to 4, and strictly less than 4. Sorry, n less than or equal to 4. So there's a bit of discussion on that, but I won't get into it. Okay, so in terms of this notation, example, the Tate curve, EQ, can be thought of as a G1, 1, G0, 1, okay, G1, 1, maybe they're the same. Point of Z cube. ZQ valued point of G0, 1, G1, 1. Right, because it's a generalized elliptic curve, Tate curve. We saw that in an example. So it's a value point, and therefore you have a map. Think of it as a point, saying that there's a map from spec Z power series Q to X0 n or X1 n. And this induces map of formal schemes such. Okay, so I'm going to use this morphism a bit later. It's a nice morphism. N is 1, sorry. Q expansion principle is very simple. The principle behind the Q expansion principle is very simple. Needs a little bit of technology before we get there. Trying to do it. Okay, so variant 9.3.6. Diamond M. Again, instead of using point of order n, which is an embedding of Z mod n inside E-reg, you can look at embeddings of mu n in E-reg. Looking at a different functor, but using instead these kind of embeddings. You get another model. X mu of n. Mu is Diamond M's notation, which is defined over Z again. There's a slight advantage in using this. For Z is the whole point. So even though in this, maybe in this workshop, we haven't been using this alternative formulation, this is the one that we'll use for the Q expansion. All right, and so you can also define TP on this model, which I won't get into. I think I defined TP explicitly enough times, but one could do it a few more times, one at a time. Okay, so finally the punchline, the Q expansion principle. All right, so we're finally in chapter 12, where the Q expansion principle is, section 12.3 of Diamond M. Okay, so some motivation first. So we already know that we have Q expansions of the complex numbers. So space of modular forms, classical modular forms of weight K and level N, gamma 1n. We know that there's an injective map into C power series Q. Infinity to expansion of F. Okay, so let's make the following definition. And there's various kinds of M's in this development, so I hope I can keep them straight. Script M's and Roman M's. So first, let's define the modular forms. The words are very important here. Modular forms with coefficients in Z. And then there's going to be something called modular forms over Z, and we're going to show they're the same. But for now, let's define modular forms with coefficients in Z to be the preimage of ZQ under the Q expansion map. Okay, so for all we know, this space could be zero, right? There may not be a single modular form whose Q expansion lies in Z, right? We don't know that this space is interesting. We know it's interesting because, at least over Z bar, we know it's interesting in weight 2 because we proved that using the Jacobian. Using the Eichler-Schumer map, for instance, you know it's interesting because sure there was an integral structure, etc., over Z bar. But suppose we had forgotten all that, we don't know any of that, and we define this space of modular forms with coefficients in Z. Now, similarly, you can talk about modular forms with coefficients in any ring just by tensoring the previous line with A. So, as I said, these are going to be called modular forms with coefficients in A. It's just a definition. It may be the zero space. We don't even, I mean, this is even a bit weirder because if this is zero, then it's going to be zero for all A. Turns out that this maps into AQ objectively. Okay, so the first order of business is to make that space precise. And for that, we needed these canonical models. Okay, so to make these spaces precise, integral spaces of modular forms, make these spaces precise, need the following algebraic geometry definition. Yes. Forms. Yeah, so they just say this. I was thinking about it, but they say it. But anyway, it's not really important. They say something about torsion not happening or something. Yeah, but we don't really need this. Actually, I'm going to define it formally now. This is just a motivation. We're going to define one Q expansion map, and there's a theorem that is injective. So you can just think of that. They do say it is injective though. And I didn't find any typos in that paper, so they're probably right. But I was wondering about the proof too. Okay, so what is the algebraic geometry definition of a modular form? This is a sort of fancier definition of a modular form. So I'm going to not be able to define anything. Well, basically, there's sections of some line bundle on this scheme. Okay, so let me write some things down. You take the pullback under the zero section. So we're going to use this variant model, x mu n to E universal of sheaf of relative scalar differentials. And the definition then is, so this is, I think Katz's definition maybe. I forget now. MK gamma 1n of A for any ring A. So remember, this was over Z, and you can do the whole thing over A for any ring A. So I'll adorn things with a little a without further comment. I'm working over A. So it's the space of global sections of this line bundle. This, to be distinguished from that, so these are going to be modular forms with coefficients in A, and these are going to be modular forms over A. Distinguish the two. They're soon going to coincide, and that's one of the main results. Sorry, yes, X mu here. Thank you. Using this model. Okay, so what is this line bundle? Yeah, I could try and motivate it here maybe. So you have an action of gamma 1n on H cross C. You can't see probably because I'm writing small. Actually, why am I off the camera? It's correct. So let me just write it here. But I wasn't planning to spend time on it. So H cross C to H. You have an action of gamma 1n here, where gamma 1n acts in the usual way on the upper half plane. Let me not write lots of things. And it acts by multiplication by j gamma tau. So on a point tau comma z, it acts by multiplication by c tau plus d, okay, on the second factor. And you can project to the first coordinate. J gamma tau not z. J gamma tau, I think I've not defined. So then we see the usual c tau plus d. Everybody knows that. So you can think of modular forms as, what is a modular form? It's a section of this, it's a line bundle, one-dimensional fibers here. If you wanted to write down a map going the other way, so that projection with this map is the identity, but on the first factor, you don't have much choice. It's just induced by projection with tau z maps to tau. On the first factor, you don't have much choice when you take the section, right? You have to take tau to tau, but here you have some ambiguity, right? So if you write what that ambiguity is, it turns out to give you exactly the definition of a modular form. If tau maps to f of tau, you can check that you'd have to have, because of well-definedness using those representatives, etc., you'd get a definition, the definition of the modular form. So sections of this bundle are basically equivalent to modular forms, and this is mimicking that. In fact, we're going to use this. I've only done on the open thing here. One can compactify, and that's done in Diamond. We're going to use the fact that this line bundle coincides with the compact version of that line bundle, or the complex numbers eventually. Okay, so some facts. Yeah, we're going to use it right now, actually. If you look at, so the script M, did I write a script M? Yeah, this is supposed to, I should have emphasized that. The script M to distinguish it from the Roman M's. So script M, gamma 1 and C is exactly equal to the old space of modular forms. If you're working with the complex numbers, this line bundle collapses to a line bundle of this kind. A compact version of that line on the compact space. And so you get exactly your classical modular forms. So this is why this is a good definition, first of all. You recover at least your classical modular forms of the complex numbers. Second fact. Because you're in some algebraic geometry setting, you have some nice properties with respect to tensor product. Take a look at modular forms over A and tensor them up to B. You wind up getting modular forms over B. As long as some minor conditions are true. For example, if B is A flat is one of them, but let's write a simpler one. A is bigger than 1 and 1 over n belongs to B. So we're going to be working with A to be Z and B to be the complex numbers soon. So 1 over n is certainly in the complex numbers. Okay, so right, so let's go back now to, those were some generalities on modular forms over various rings. So now consider the following picture. So we have this notation now, this x keeps changing, x of n. And let's look at this, the moduli space of moduli scheme for elliptic curves and an embedding of mu n into, or generalized elliptic curves and embedding of mu n into the regular points. So let's look at this point, E1 over Z, and mu n sitting in E1 over Z, sits in GM. Right, so that's a point on this scheme. Therefore, it corresponds to a morphism from spec Z. I'm in an M called little s infinity. Supposed to be the cusp at infinity. But we already saw another way to think of the point at infinity, at least when n was 1. So what about the Tate curve? That corresponds to the following point. The Tate curve was another scheme over spec Z over Z power series Q, so therefore over spec Z. And here you just take the canonical embedding. Right? C star mod Q has the nth root of unity sitting in it. Something like that. So mu n sitting in EQ. So this corresponds to this point. And as we said, if you put Q equals 0, then this morphism is just induced by Q equals 0. You get a map like this. You get that this diagram commutes. So the Tate curve specializes when Q equals 0 to that point. A little confused as to why there's not a P1 with a double point there, but okay. All right, so we have this picture. So as before, we get an induced map. From formal completion, isomorphism to x hat mu n, x mu n hat, the completion along S infinity, image of S infinity, the closed immersion. Okay, so we just saw this for n equals 1, but we got some isomorphism like that. All right, so now we can almost define the Q expansion map. So let omega hat, maybe I can write it here. So there was an omega over here, the line bundle, and omega tensor K, etc. So similarly, we have omega K hat, completion of this line bundle. And on this side, it turns out to correspond to something simple, just a free module of rank 1. And moreover, it's generated by some canonical element, which is just slightly mysteriously called omega canonical tensor K in diamond M. I guess it's something like dq over q. So I didn't have time to look up the literature, but this is some official definition of omega canonical due to cats, some canonical generator. Maybe I should put a, yeah, no, this is just a generator. Okay. That's not a. So from this, we get the expansion map. So from 8, 0, so modular forms were just sections of this bundle. Let's work over A again. Sections of this line bundle. 2 sections over the formal completion. And since this is free of rank 1, this is just given by A power series Q times omega canonical. Right? This is a generator of that space. Free of rank 1, and up to that generator is just given by this power series. So let's give this map a name. If you drop the omega canonical tensor Q, you just get a map. Expansion map. So iota or I, or phi, sorry, not for Frobenius, phi infinity A. Okay, so basically what you're doing is you're looking at some differential form and restricting to some neighborhood, formal neighborhood at infinity. And there, things are simple. Everything is generated by one element. And this is the section. This is what you get when you restrict. Okay, so finally, some theorems about this map. And then we're done with the Q expansion principle. That means 5 more minutes, right? 5 more minutes. Good. I think I'll finish on time, actually. Okay, great. So, first of all, phi infinity A is injective. This is what Chandrakant was asking about. But with this, oh, sorry, I should have written, nobody complained, script MK. Gamma 1A. These are the algebraic geometry definition of modular forms. A omega hat, where? Ah, yes, there's a sub A here also, yes. A and A. Everything is over A. Every ring is a Z scheme, so do some base changes. Okay, so what is some parts of this theorem? The first one is that this map is injective. And the second part is that actually this map, so the space of modular forms coincides with the space that we had before. So more precisely, the following diagram commutes. To write injective, assuming part one, these things are injective. So we have phi infinity A, and similarly we have phi infinity B. Those B is in A algebra. Then we have this map just from answering with B. Here you have also an H map. Let's take A sitting in B or something like that. Simple case. So the claim is that this diagram commutes, which is just a fancy way of saying that, i.e., the image of script MK gamma 1n A in MK gamma 1nB consists exactly of the modular forms over B with Q expansion in A. I hope you can see this. The image of this map is exactly those modular forms whose Q expansion lies in A. So in particular, applying that with A is equal to Z and B is equal to C, corollary that I forget the first word I used, modular forms, one was over A and the other one was coefficients in A, right? Those two notions coincide. So the image of, just copying that sentence again with specializing to A is equal to Z and B is equal to C. We said was MK gamma 1C, gamma 1n, the usual space of modular forms. Is exactly the old MK gamma 1n Z, which may have even been 0. Okay, so these were the modular forms whose whose Q expansions were in Z, pre-image of Z power series Q. Modular forms with coefficients in Z. So these two notions coincide, so that's great. So we're on firm ground here. That means that some space of modular forms that will still could be zero, but we'll see they're not right now in a second. Some space of modular forms which a priori could have been zero will in fact now not be in zero. Theorem that we get out of this, for all n greater than or equal to 1, mk gamma 1n has a basis over Z. Why? So this proof, which is very slick, doesn't work for n equals 1, 2, 3. For those cases, you have to do it by hand. We already mentioned the case n equals 1 many times, how to do it by hand. Write down some explicit basis over Z. So we'll get into explicit things here. And for n greater than or equal to 4, we can use the definition of these algebraic modular forms, algebraic geometry definition of these modular forms. So first of all, we know this. Because k is greater than 1 at least. Let's assume that 1 over n belongs to the complex numbers, so we can use what I'm just erasing right now. To say that when you tensor this with C, you get mk gamma 1n C, which mk gamma 1n, usual modular forms. And by the corollary, this was exactly mk gamma 1n Roman n Z, modular forms whose Q expansion was in Z. Okay, so in particular, this space has to be non-zero, right? If that space is non-zero, tensoring up to C, we get that space. Okay, so this is the sort of algebraic geometry proof of the fact that the space of modular forms has a Z structure. So you've seen various proofs now. I'm sorry if I was a little pedantic doing this. Maybe one could have said this in 5 minutes also, but I thought maybe one should spend some time doing some of the background also. Notice there were no Heck operators in any of this, just a Z structure. That's not an eigenbasis or something. These are not, your eigenforms may not be defined over this space. Might be defined over, the Heck operators will turn out to preserve this space. We didn't do the modular interpretation, the interpretation over Z of the Heck operators, but they will preserve that space. So great, so that's the Q expansion principle. I hope that helps you retrospectively fill a gap in Samuel's course. Okay, thank you.
Any questions? Comments?
Yeah. Yes, yes, yes. Oh, yeah. Actually, they give 2 or 3 different formulations. So it actually does work for weight 1 also. I think it works for weight 1 in this context. I was a bit lazy. Yes, it does work for weight 1. So they have 2 criterion for base change, that the space of modular forms over A tensor with B is the space of modular forms over B. So one of the criterion is that the weight is bigger than 1 and 1 over n belongs to the bigger ring. And the second one is that B is A flat. So this is just, so that works for all weights. So I think one can do that also. Are there people interested in weight 1 forms here? You spend your life doing weight greater than 2, then suddenly you think, okay, I should write a paper on weight 1. Yeah, so I think yes, that's true. That is true. That is true. That's yeah, because of flatness. Yeah. Yes, you can have the Q expansion map being like the Eisenstein series, the weight P minus 1. Q expansion of that mod P is just 1. That's true. So that's not injective. But yeah, okay. So one should be a little, we can talk about this more. We should be a little careful about weight 1.
Any more questions, comments? Well, then, on behalf of the participants and the organizers, I would like to thank Professor Ghate for this wonderful set of lectures. Let's give a big hand.